Okay, moving on from the photoelectric effect, Einstein's theory of the photoelectric effect, let's talk about the Bohr atom. So Bohr was developing a theory to try to explain something that is referred to as the Rydberg formula, which is this formula here. That the frequency of light emitted by hydrogen atom in a discharge tube like this is given by some constant times an expression that involves two integers, n1 and n2. So 1 over n1 squared minus 1 over n2 squared, where n1 and n2 are integers, and n2 is greater than n1. So this reproduced nicely the emission of several lines observed in these discharge tubes where you have a low pressure of some gas like hydrogen. In this particular case, it's about hydrogen, although you can come up with similar expressions for other atoms as well, other gases. But if you apply a voltage to this, then a plasma develops and there's a glow, and you can disperse that glow through a diffraction grating and look at a screen, and you see a series of lines. And also the sun has a similar series of lines, but they're dark lines at the same wavelengths that you see in one of these discharge tubes. So there's a series of lines. Perhaps you've done this experiment looking at a discharge tube through diffraction grating, a little piece of film, and you see these interesting lines that appear. And Bohr's model was an attempt to try to explain, to try to come up with a physical explanation for this Rydberg formula. This Rydberg formula was just sort of empirical. It worked really nicely to reproduce the spectra that include dozens of lines, these very sharp features in the spectrum. And it's a very nice, simple, elegant formula, so it hints at there's something deeper going on here. And so Bohr, at this point, it was known that atoms had things like electrons, and the theory of electrostatics was well established, and electrodynamics, electromagnetism was well established. And so Bohr was trying to explain this result in terms of some model that uses electrostatics. And he assumed that, okay, if electrons move around an atom in specific orbits, or move around the nucleus in a specific orbit, then if they're in that sort of fixed orbit, kind of a planetary orbit, then the kinetic energy of the electron has to balance out the attractive Coulomb potential at that orbit. And at this point, the electrostatic theory said that there was a Coulomb potential of a charged particle, and it was minus e squared over 4 pi epsilon naught r, where e is the charge of an electron, and epsilon naught is the permittivity of vacuum, and r is the distance between the two charges, between the positive and the negative charge. So then if you further assume that the radii of the orbits are fixed, such that the radius of the orbit is equal to some constant times an integer squared, and that constant we'll call the Bohr radius, and it ends up being about 0.529 angstroms, or 52.9 picometers, or 0.0529 nanometers. And Bohr was able to come up with a series of arguments of various levels of credibility, of validity, that stated that this Bohr radius would be 4 pi epsilon naught h bar squared over mass of an electron times the charge of an electron squared. And these were constants that were known to some extent at this time. And the fact that he was able to assemble this theory, even though some of the arguments were a little bit dubious, it had all these known physical constants. H bar is just h over 2 pi. And it gave a pretty neat theory, and there was some of an explanation. And basically then the idea was you had these circular orbits here, like I've drawn, and when light is impinging on the system, say in the n equals 1 state, then it can promote it to the n equals 2 state, where n is this integer that sort of the number associated with each orbit. And then when it does that, it would only do that when the energy of the light is h nu, and so then that delta E for between n equals 1 and n equals 2 is going to be h nu. And that would be for absorption of a photon, but for emission of photon, it's just the reverse. You can imagine a particle being, an atom being electrically excited into the n equals 2 state, and then it drops down to the n equals 1 state, emitting a photon. And that gives rise to the emission line spectra in these discharge tubes. So this formula seemed to include some electrostatics, and it agreed with the Rydberg formula, so it seemed like a real step forward. Nevertheless, it left a lot of questions open. There were holes in this theory big enough to drive a Mack truck through, but it did seem like a step forward. That said, we know now that electrons do not move in fixed circular orbits. That may be something that you heard in middle school, or that maybe if you got the wrong lecturer in Gen Chem, they might have said something like that, but it's not true. Electrons have these complicated trajectories described by wave functions, and they're not at fixed planetary orbits. So the picture that you may have learned in middle school, or that sort of seems to be reproduced of electrons sort of zooming around an atom in these circular orbits. You see that in the logo of Bruker, which is a scientific equipment company. That's not the real truth, at least as far as we know it. The current consensus. So that brings us to de Broglie's particle wave hypothesis. And his hypothesis is that a particle in motion with some momentum p has a corresponding wavelength lambda given by lambda equals h over p. Okay, and de Broglie, we'll see where he's headed with this hypothesis in a minute. But basically his hypothesis starts with this notion that, well, if light can be both a particle and a wave, maybe actual particles with mass, things like electrons and protons and so on, also can be waves, and they could have a wavelength. It seems like an idea that's really kind of way out of left field, but sometimes that's how these things progress. So this can be derived, although it's not a very rigorous derivation, but there's a sort of line of reasoning, let's say, that goes as follows. If we start with a beam of light, we know that a beam of light has energy, right? That light transmits energy, that if you shine a light on something, it will heat up. And so we know that light has energy. Furthermore, we know from, and we also know, of course, at this point, we know that E equals h nu, So energy of a photon is equal to h nu, and that comes in just a moment. But even without that, we know that light has energy. And according to Maxwell's equations, light has a momentum. Even though it doesn't have a mass, it doesn't have a rest mass, it still has a momentum, which is kind of interesting, but nevertheless true. It's been observed many times. And it's the basis of a lot of concepts that are pretty solid. Like, for instance, there are proposed spacecraft, and they've been demonstrated on a small scale that this works, where you can actually shine a strong light on a solar sail, or a light sail, and cause an object to move. And it requires a lot of light, and it requires a very lightweight object, but nevertheless this is well known. And it can be observed in the laboratory by suspending a mirror on a very fine wire and reflecting, and you can see that the mirror can turn, showing the momentum of the photons striking the mirror. And anyway, so that the momentum, according to Maxwell's equations, the momentum of a beam of light is energy of the beam divided by the speed of light. So if we just switch to single photon case, we just talk about one of the photons in that beam. Now that momentum of the single photon is going to be very small, but we can still talk about what it should be, and even though it might be hard to measure on the single photon level. And the momentum of a photon, you would just replace E with the energy of a photon, which is h nu. And so we get that the momentum of a photon is equal to h nu divided by c. And we can also recall that energy of a photon is hc over lambda, because there's this relationship between frequency and wavelength and the speed of light, because light moves at the speed of light. And so we get hc over lambda divided by c is the momentum of a photon. Of course, the c's cancel, and we get that the momentum of a photon is equal to h over lambda. So if this is true for particle, so then de Broglie's hypothesis was that if this is true for photon, it may also be true for particles. And so if we have a particle with some momentum, it's traveling at some velocity, it has some momentum mv, then the momentum of our particle is equal to h over lambda of the particle, or we can rearrange and state that the wavelength, or lambda, of our particle is equal to h divided by momentum, or h over mass times velocity. And that if we have a very light particle, like an electron, then that mass is going to be very small. And so then the wavelength associated with that particle may be something that's experimentally accessible, maybe on the length scale of things like atoms and molecules. And so then he takes this a step further, and in that if electrons are moving in orbits and electrons are waves, then each orbit must have some integer number of wavelengths to form a standing wave. Otherwise, as it orbits around, it's going to interfere with itself destructively, and you don't get a wave, so that orbit is not allowed. A little bit like how when you're plucking the string on a stringed instrument, there are certain frequencies of sound that are emitted. And so, sort of trying to put this into a picture, if we have a wave, a little wiggly line here, and we try to wrap it around a circular orbit, then we're going to get this kind of blobby looking thing that has a bunch of waves wrapped around a circle. And because the head sort of has to meet up with the tail, then you're limited to some integer number of wavelengths per orbit, whether it's 1, 2, 3, and so on. And that can help explain the Bohr atom. It can help explain why there are certain radii that are allowed. They're the radii that are associated with some integer number of wavelengths for an electron moving around the atom. So that's all fine and well, but at this point it really seems like wild conjecture. That's when we have to turn to experiment. Thomson, Davison, and Germer showed that electrons are waves by diffracting an electron beam from a nickel crystal. And you can see these clear interference fringes when this is done. So challenging experiment, and it was done by this trio. Thomson of that trio was the son of J.J. Thomson, who was involved in the photoelectric effect and who, through that and other experiments, showed that electrons were particles. Then his son showed that electrons are waves. So it's kind of interesting little symmetry there. So now we've established that electrons are waves. And through a series of interesting hypotheses, we've arrived at this point. And then the question is, how do we develop a way of talking about these waves, a way of predicting how these waves behave, a more solid theoretical framework for these matter waves? And that's where we introduce Schrodinger's equation, or equations, next. There's actually different versions of the Schrodinger equation, the time-independent Schrodinger equation and the time-dependent Schrodinger equation. We'll mostly be talking about the time-independent Schrodinger equation. That's really what's talking about these kind of standing waves. And time-dependent Schrodinger equation, very important in systems that are changing over time. But first we want to talk about sort of stationary systems, and so we'll talk about the time-independent stationary version of the Schrodinger equation, and that's in the next lecture.